Welcome back to Calculus 2. In this lecture, we're going to introduce another test for determining when an infinite series converges or diverges, called the integral test. All right, let's start by considering this example, this infinite series, where the term is given by 1 over n squared, starting with n equals 1. Notice the terms here are getting smaller, like what we saw earlier in the previous lecture relating to the divergence test. What we're going to try to do here is visualize this and how the terms can be visualized coming from a continuous graph. That's going to transition us into a familiar integral of a function. All right, so we can just start by plotting those terms. The terms here start off with 1, then 1 over 2 squared would be a quarter, 1 over 3 squared, 1/9, and then so on and so on. So this graph is not to scale, but it will work. And you can see there, starting with the first term, 1, the values decrease rather fast. Now, how we're going to make a connection to get an integral, like we would think of for a function f of x, a continuous function, is we're going to keep in mind that the terms here are discrete values coming from a discrete function where we plug in integer values 1, 2, and 3, but they sit on top of a continuous function f of x where we could plug in any real number, not just the integers. So here, since our terms come from the form 1 over n squared, we might see this being related to the function f of x defined as 1 over x squared. Basically just replace x with n and we get our general term coming from 1 over x squared, replacing x with n. Now this graph here, you can see it decreases very rapidly. There is a vertical asymptote at 0 for this function, but we're not going to be concerned about that since our infinite series starts with index value 1. Now, how we're going to make a connection to getting an integral from this is we're going to notice that all of our discrete values for n are 1 unit apart. And what we're going to try to do is put some rectangles where the width is 1 unit underneath this graph. If you think back to your Calc 1 course, here what we're introducing is basically the right endpoint approximation of an integral using rectangles. So if we split the x-axis into intervals of length 1 unit, going from 0 to 1, 1 to 2, 2 to 3, 3 to 4, all the way down the entire x-axis, the first right endpoint at 1 gives us a height of 1 over 1 squared, which is 1. All right, the second rectangle there, going from 1 to 2, the right endpoint is at x equals 2. Plug that into your function, you get the function value or height 1 over 2 squared, which is a quarter. Now think back to Calc 1, we can find the area of each rectangle by multiplying the width, which is 1 for all of them, by the height coming from the function value. And we can see here, add up the total area of all those rectangles. There's an infinite number of them since the graph keeps going down the x-axis. We get an infinite series here, which is our infinite series in question from our example above. Notice the multiplying by the width, which has the value 1, doesn't really do anything, but it makes a connection for us from an infinite series to this integral, thinking of it as approximating area beneath a curve. All right, well, what's the benefit of doing this? Well, let's take a look at this infinite series, 1 plus a half squared, plus a third squared, plus a quarter squared. And we're going to basically take a look at those rectangles and notice that they are all below the graph, the graph of the continuous function, that is. And what that means is the integral from 1 to infinity, so the integral of the continuous function f of x, that's going to be greater than all of the rectangles which are below that graph. This would be the case of an under approximation with these right endpoint approximated rectangles. Now, to make this consistent, notice the integral goes from 1 to infinity, and we still have that first rectangle, which lies over the x values from 0 to 1. The length of that, or width of that rectangle is 1. The height is 1. 1 times 1 is 1. So the area of that first rectangle is 1. And what we can see here is that all of those terms from our infinite series are less than 1 plus the improper integral from 1 to infinity of 1 over x squared. Why are we looking at the function 1 over x squared here? That is the continuous function from which our terms a sub n of the discrete function come from. And what we can see here is what we get in that improper integral from 1 to infinity. Think back to a previous lecture that we covered with improper integrals. This is what we call a p integral, where it's 1 over a power of x, where the integral goes from 1 to infinity. So in this case, the exponent value is 2. This gives us a convergent p integral. Recall, p integrals converge where the power p is greater than 1. Now, if we combine this with some ideas before with comparison tests for improper integrals, basically what we can see here is our infinite series, all of those rectangular areas, all infinite of them, that is going to be less than 1 plus the value of that improper integral. The value of the improper integral is 1. So what we can see here is our infinite series, all the terms being added up, is less than 2. And what that means is we have a bunch of terms less than 2. That means the infinite series, when we add up all those terms, since it's less than 2, those terms have to sum to a finite number, since it's less than 2, which is also a finite number. This is just a more complicated way of saying we can conclude that our infinite series, 1 over n squared, is convergent. And that's because our improper integral related to this general term, a sub n, the function 1 over x squared, that leads to a convergent improper integral. So essentially what we're going to be doing with the integral test is we're going to start with an infinite series and then turn it into a related improper integral of a continuous function, f of x. We're going to make this more precise in what comes next by giving the formal statement of the integral test, but this is a very nice, simple example to kind of motivate why you should believe the integral test or why it's true. All right, now the precise statement of the integral test that we have here is actually a little technical. Like most theorems in mathematics, there are some conditions that have to be satisfied in order for you to reach the conclusion of the theorem. So here, the conditions of the integral test are we have a function that is continuous, positive, and decreasing on the interval 1 to infinity. So keep in mind some basic ideas of what continuous functions are. Their graphs have no breaks, gaps, or holes in them. The good news is most functions that we'll encounter in the standard courses of the calculus sequence, most of them are continuous with a few exceptions. The part about the function being positive just means basically that the graph of our function is always above the x-axis on the interval of x values from 1 to infinity. And the decreasing part just means that the function values keep getting smaller as the values of x get bigger. Now, this goes back to our intro example that we covered a few minutes ago, where we said our function f of x was 1 over x squared. We turn our continuous function f of x into a discrete function, an nth term, general term, a sub n, basically just replace your x with n. So if we do that here and define a general term, a sub n, as f of n, so basically just plug n in as your variable instead of x to your function f, we get a term for an infinite series. And shouldn't be surprising from what we saw in the intro example, we reached two conclusions The first is if the improper integral from 1 to infinity of our continuous function, if that is convergent, then the infinite series with that general term a sub n coming from that function is also convergent. We have a similar related result. If the improper integral of the function is divergent, then the infinite series is divergent. So it's a nice correspondence between the improper integral and the related infinite series. So keep in mind for the integral test, these three conditions have to be satisfied in order for the conclusion to be reached. If any of the conditions aren't met, then we can't get the conclusion here. So the integral test wouldn't apply if, for instance, 2 out of those 3 conditions are met. All right, just to mention a few important remarks before we move on to some examples. This all sounds fairly complicated, perhaps, but how we turn an infinite series into an improper integral, basically just take your general term, a sub n, and you can convert it to a function, f of x, just replace anywhere there's an n with x, and that converts it from a discrete function, a sub n, into a continuous function, f of x. All right, so just to take a look at an example before we get to some like real examples. Let's say we had the infinite series where the general term, a sub n, is 1 over the square root of n. All right, and we're going to convert that into an improper integral. Take your general term for a sub n, replace the n with x, and we get this continuous function, f of x, 1 over square root of x. And what the integral test would have us look at is the improper integral from 1 to infinity of that function, 1 over square root of x. Here, the thought is we're introducing something new, infinite series, and the integral test converts them into things that are familiar, improper integrals. That's what we covered earlier in the course. All right, a second remark or comment I want to point out is one of the conditions. How do we know when a function is decreasing? This is the most complicated of all 3 to check. Usually it's pretty easy to determine if the function is continuous and positive. The decreasing part is a little trickier. Think back to your Calc 1 course. At some point you did learn about increasing and decreasing functions, and that was related to the sign of the first derivative. And you might recall a function is increasing if its first derivative is positive on an interval, and a function is decreasing if the sign of its first derivative is negative on an interval. So how are we going to know if a function f of x is decreasing? We're going to check that its first derivative is negative on our interval, usually from 1 to infinity. All right, a third comment, which is going to be what makes these examples go really quick with the integral test. While we convert an infinite series into an improper integral, we don't actually have to fully evaluate the improper integral. Recall, we had some comparison tests for improper integrals. And that's going to be a really nice shortcut that allows us to bypass some integration methods and just quickly determine if our improper integral is convergent or divergent. We're going to see that in action in some examples that follow. All right, and a fourth and final comment, which is worth pointing out, if you do evaluate your improper integral and you come out with a number, in other words, the improper integral is convergent, the value of the improper integral is not the value of the sum for the infinite series. So just be cautious of that. You might be able to evaluate the improper integral, but the value is not the sum of your infinite series in general. All right, let's take a look at some examples to see how we apply the integral test. So for example 1, we'll take a look at 2 parts here. The integral test basically asks us to determine if an infinite series converges or diverges, where we're just given an infinite series to start with. All right, let's go through part A so we can see how all this comes together. Our general term here, a sub n, is 1 divided by n cubed plus 1. Now, on our interval from 1 to infinity, this function is continuous. There's no breaks, gaps, or holes in the graph if we were to think of that being related to the continuous function, f of x equals 1 divided by x cubed plus 1. There is a value of x for which the denominator becomes 0, for which the function has a vertical asymptote, but that wouldn't be in our interval from 1 to infinity. The denominator would become 0 when x, or n, is -1. And negative values aren't in our interval from 1 to infinity. So this is going to be continuous. The values here of 1 over n cubed plus 1 are always positive. Notice our indices, n, all the values are positive integers, 1, 2, 3, 4, and so on. And while you get fractions, all the fractions from this general term are positive. And the decreasing part is also, I think, simple to see. Notice the general term is of the form 1 over a quantity, n cubed plus 1, where the quantity is getting bigger as n goes to infinity. Now, when you have a fraction where the denominator gets bigger, the fraction as a whole gets smaller. So as n gets bigger, this general term gets smaller. So this function is decreasing. These three conditions are the same conditions of the integral test. So for this infinite series, since all three conditions are met, we can apply the integral test. So what we do is convert this infinite series into a continuous function's improper integral. Since the indices go from 1 to infinity, we have an improper integral from 1 to infinity. And if we convert the n's to x's, the general term 1 over n cubed plus 1 converts to the function 1 over x cubed plus 1. And what we now try to do is determine if this improper integral converges or diverges. All right, and this is where we're going to use the comparison test for improper integrals. We're going to notice here that we can get a bigger function by making the denominator smaller. 1 divided by x cubed plus 1 is less than 1 over x cubed. The benefit of doing this is now this bigger improper integral from 1 to infinity of 1 divided by x cubed. This is a convergent p integral. The power here, p, equals 3, which is bigger than 1. And this tells us that our integral, which is less than this, is also convergent by using the comparison test. So what we've determined by using the comparison test for improper integrals is that our improper integral must also be convergent. And since our improper integral is convergent, the related or associated infinite series with the term 1 over n cubed plus 1 is also convergent by the integral test. Now notice the work is actually pretty minimal. It just requires you to be on top of some previous results, understanding improper integrals, recalling what the p integral is, how we use the comparison test. So if anything is a little complicated right now, you might want to go back and review what we covered on improper integrals in a previous lecture. All right, let's take a look at a final part B here. We can convert our function, the discrete function, a sub n, n divided by n squared plus 1 squared, into a continuous function, replace all n's with x's. And this now is not as obvious that it is decreasing. It's certainly continuous on the interval from 1 to infinity. The denominator here, x squared plus 1 squared, is never going to be undefined. X squared plus 1 equals 0 has no solutions, that are real numbers, that is. So this is going to be continuous. Our values of n and therefore x are on 1 to infinity. So plug in values for x from 1 to infinity. this fraction will always be positive. Here, it's not as obvious that this is a decreasing function. Now, what I'd like you to do, pause the video for the continuous function f of x here, differentiate that function to find the first derivative. Use a combination of quotient rule and chain rule, and you should be able to get the derivative f prime. We'll check in about a minute or so. Welcome back. If you correctly calculated the first derivative and simplified it, you should find that you get for f prime 1 minus 3x squared in the numerator, and then x squared plus 1 cubed in the denominator. Keep in mind, for the quotient rule, you have the function's denominator squared, so that would give you x squared plus 1 to the 4th power. But if you fully simplify your first derivative, you should find that 1 power or factor of x squared plus 1 cancels out between numerator and denominator. All right, so what's the point of this? Well, notice our n values go from 1 to infinity, so the values of x we're considering go from 1 to infinity as well. And for values of x that are greater than or equal to 1, notice that numerator, 1 minus 3x squared, that numerator is going to be negative when x is greater than or equal to 1. And what that means is now that the derivative is going to be negative when x is greater than or equal to 1. And since the derivative is negative, that tells us that we have a decreasing function. So at this point now, all 3 conditions are met for us to apply the integral test. All right, this one, again, we can do quickly with a comparison for improper integrals. The improper integral that we're getting from converting our infinite series is the improper integral from 1 to infinity of the function x divided by x squared plus 1 squared. Now we can again use our same trick. This kind of looks like a more complicated version of a p-series, so we might try comparing with a p-series. We can find something bigger than this, than our function, by again making the denominator smaller. We can make our denominator smaller by getting rid of the plus 1 in the denominator, and we would get now the function for which our improper integral is less than. We get the function as x, the original numerator there, but now it's going to be in the denominator x squared squared, giving us x to the 4th. Since we're getting rid of the plus 1, we're making our denominator smaller to get a bigger fraction. All right, that whole mess, x divided by x to the 4th, that simplifies to a simple reciprocal power, 1 over x cubed, which is, again, a convergent p integral, since the power p, 3, is bigger than 1. And if we work backwards, by comparison, our improper integral must also be convergent, since it's less than this convergent p integral. All right, if we pull all the results together, since we've now determined by comparison that our improper integral is convergent, the integral tells us that our infinite series from 1 to infinity of n divided by n squared plus 1 squared, that must also be convergent. All right, and that's pretty much how we apply the integral test in some examples that we can actually evaluate pretty quickly using the comparison test for improper integrals. There might be a few examples in the homework where you might have to resort to direct evaluation of the improper integral, but for a lot of examples, the comparison test will make quick work of them. All right, before we finish this lecture, we've been mentioning the p integral a lot from improper integrals, and what we actually get now from the p integral is a related infinite series that we're going to call the p series. All right, and the p series, we're going to define it as an infinite series from n equals 1 to infinity, where, like the p integral, we have 1 over a power of x 1 over x to the p. Now, for an infinite series, our variable is n. Our general term will be 1 divided by n to the p. And what we get for our terms here are 1, that is the case where n equals 1. And then you get 1 over 2 to the p, plus 1 over 3 to the p, and 1 over 4 to the p. And that continues forever since we have an infinite series. Now, combining what we know about the p integral with the integral test, we actually get some pretty nice conclusions for our new p series. The p integral was convergent when the power is greater than 1, and it's divergent when the power is less than or equal to 1. If we combine this with the integral test, what we find is the p series is going to be convergent also when the power p is greater than 1, and the p series is divergent when the power is less than or equal to 1. All right, let's take a look at some examples that we've covered before. The first and primary example I want to bring up as being a p series is what we introduced and called the harmonic series, where it was the general term 1 over n. Now, this is a p series. It's the case where the power p equals 1. Now, it was a little complicated at the time for us to see that the harmonic series is divergent by looking at the sequence of partial sums, but we did see that it was eventually divergent. Now, with the p series, we can see easily that this is divergent. The power for p equals 1, since we have just 1 over n, or 1 over n to the 1. And in this case, where the value for p is less than or equal to 1, the p series is divergent. All right, if we go back to our intro example, where the general term was 1 over n squared, this is a p series in the case where p equals 2. And since the power is greater than 1, our infinite series here is convergent. Now, this is one of my favorite infinite series in mathematics. The sum is pi squared divided by 6.